we propose LAPIG, a language-guided projector image generation method with surface adaptation and stylization. Projection mapping is a versatile technology that transforms the appearance of objects into dynamic displays by projecting digital images or videos onto them. And it typically involves pre-designed projections, requiring creators to have the skills to achieve visually pleasing effects. Furthermore, due to the complex environment, object material, and device optical properties, directly projecting desired patterns onto the target object may suffer from photometric and geometric distortions. Therefore, most projection mapping applications rely on projector compensation techniques to cancel the distortions. However, due to the projector's physical brightness limitation, not every projection surface is fully compensable, especially those extremely dark and bright regions. This is because the extremely dark or bright projection surface regions absorb or reflect more light. Even when the projector brightness is set the highest or lowest, the surface texture cannot be fully compensated. To address this issue, we propose LAPIG, a language-guided projector image generation method with surface adaptation and stylization, which consists of a language-guided style transfer module for user-controllable surface stylization and a projection surface adaptation module for compensable stylization. LAPIG is the first language-guided projector image generation method that can not only stylize the projection surface, but also adapt to it. LAPIG non-trivially integrates user language-guided style transfer, project and capture simulation, and projector compensation, enabling gradient-based optimization for projector image generation. We propose projection consistency and color saturation losses to measure compensation quality and guide PSA optimization, and they are expected to facilitate other projection mapping applications. Projector compensation aims to counteract distortions caused by environmental factors, equipment, and projection surfaces, thus improving the viewer's perception of projection effects. Rasker and co-authors achieved projection on non-flat objects using geometric corrections paired with camera radiometric calibration. In practice, while camera radiometric calibration is straightforward, recalibration becomes crucial when projector settings like brightness, contrast, or color profiles are altered. To address these issues, Grundhofer and EY developed a robust, error-tolerant photometric projector compensation method using a pixel-wise thin plate spine to utilize RGB sampling images. Huang and co-authors achieved visually satisfactory projections by exploring properties of the human visual system. Huang and Ling reformulated the physical project and capture process and learned the geometric and photometric compensation functions using deep neural network. Huang and co-authors extended these capabilities by focusing on high-resolution compensation, enhancing the accuracy and visual fidelity of projections on complex surfaces. Recently, Kusuyama and co-authors proposed a projection system that optically eliminates cast shadows in projection mapping. Project and capture simulation simulates the physical project and capture process of procams. Early methods focus on light transport matrix, which models the irradiance of each camera pixel as a linear combination of the radiances of all projector pixels. To improve relighting efficiency, Huang and Ling proposed an end-to-end trainable model that explicitly learns the photometric and geometric mappings involved in the project and capture process. Errol and co-authors first formulated procam simulation using a neural radiance fields framework. Neural style transfer was initially introduced by Gades and co-authors, who proposed a method of blending content and style features extracted through deep convolutional neural network. Other related works include style transfer models based on generative adversarial networks, which can perform image-to-image translation without paired data. Reed and co-authors began exploring the use of simple text prompts to guide the style and content of the generated images. Brooks and co-authors integrates text prompts with Pix2Pix models, allowing users to apply fine-grained modifications to images according to textual instructions. To our best knowledge, there is no method that can perform language-guided projector image generation with surface adaptation and stylization. The goal of our LAPIG is to achieve projection surface stylization, according to the user input text prompt T, where I is the desired viewer's perceived surface stylization effect, and F theta is a language-guided neural style transfer model parameterized by theta. We design LPS to measure the color saturation error due to the projection, that is, any pixel value outside the range of the darkest I minor and brightest I plus images captured by the camera is unattainable due to the projector's brightness limitations, and should also be regarded as saturation errors. Then, we apply projector compensation pi dagger to eye to get the compensated image eye star of the projection surface. We design LCS to measure the color saturation error due to projector compensation, that is, pixel values outside the plausible RGB value range from 0 to 1 are counted as saturation errors. Finally, we simulate the real-world project and capture process pi hat, project the compensated image eye star to the projection surface, and get inferred captured projection eye star hat. We wish the final camera-captured projection eye star matches the desired effect eye, so we design LPC to measure the similarity between the simulated and desired surface stylization effects. Afterwards, the 3 compensation quality metrics are calculated and backpropagated to update the LGST model parameters theta. Since the accuracy of the real project and capture simulation pi hat and the compensation model pi dagger directly affects the final surface adaptation quality and the viewer's perceived effects, we quantitatively and qualitatively evaluate the accuracy of the simulation by comparing the simulated camera-captured compensation, that is, I star hat, with the real camera-captured compensation I star tilde. The results are shown in the figure. To explore different project and capture models, we adapted CompenSD to simulate the project and capture process by swapping its input and output, and we name it CompenSD reversed. The advantage of our PCNet over this adapted CompenSD model is demonstrated by comparing the two methods in the table and previous figure. Clearly, PCNet outperforms CompenSD reversed by a great margin in PSNR, RMSE, and SSIM. The effectiveness of PSA is demonstrated in the table, where with PSA shows superior PSNR, RMSE, and SSIM compared to without PSA on 5 different surfaces with 10 different text prompts. Selected surfaces are shown in this slide. These 2 rows show stylization of the same projection surface using 2 different text prompts. The first column shows the original projection surfaces. The second and fourth columns are stylized projection surfaces by LAPIG with or without PSA, given the user input text prompt on the top of each surfaces. The third and fifth columns present real captured scenes under projection with or without PSA, that is, the second or fourth column projected onto the first column after projector compensation. These 2 rows show stylization of 2 different projection surfaces using the same text prompt. Clearly, our PSA can adapt the stylization to the surface by showing fewer discrepancies between the target stylized surface and the real captured projection. The effectiveness of different PSA losses is also demonstrated in the table, where with PSA shows superior PSNR, RMSE, and SSIM compared to without PSA on 3 different surfaces with 5 different text prompts. This slide shows failure cases of our LAPIG. For Wood and Sakura, the real captured projections of in the third look different from the second row, indicating failed projection surface adaptation. For Stripe, although the second and third rows look similar, but the LGST-generated stylization failed to represent Van Gogh oil painting style. Future work could focus on improving the accuracy of project and capture simulation and projector compensation techniques, along with designing and training LGST specifically for projection mapping applications. During PSA process, we can see in this image on the far left the iterative optimization process with compensation and project and capture simulation, and observe the change in the inferred captured projection. When optimized, target textured surface will go through stylization by projector. This slide shows how we made Mona Lisa smile. This slide shows more results. In summary, in this paper, we proposed LAPIG, the first language-guided projector image generation method with surface adaptation and stylization, enabling gradient-based optimization for projector image generation. We propose projection consistency and color saturation losses to measure compensation quality and PSA optimization, and they are expected to facilitate other projection mapping applications. Thank you for watching.